Just to remind you that so we do a quick recap. So if f of x is equal to ln u, its derivative comes as u prime over u. An example for this is find f prime of x given a f of x is equal to ln 3x squared minus 1. So to differentiate this one, you say you differentiate the inside function using power rule, you get 6x and divide by the whole function 3x squared minus 1. Another one, if f of x is equal to ln sine x, to differentiate, you differentiate sine, you get cos and divide by sine. You can write it as cot if you want.
Hello? Hello?
And then this was the first reminder. Second, if f of x is equal to log base a u, to differentiate this one, you use you change the base first. In case you've forgotten the general one, so you change the base to ln. So you have log EU over log EA. But log E is the same as ln, so you have ln U over ln A. Meaning that the derivative of f will be 1 over ln A, a constant, then you differentiate u and divide by u. An example of this format, say, okay, find f prime of x. F of x is equal to log 2 x squared plus 1. So you say, okay, the derivative of this guy is equal to 1 over ln 2. Then you differentiate x squared. You get 2x. You differentiate 1, you get 0 over x squared plus 1. Another one, f of x is equal to log 3 sine x. You differentiate, you get you differentiate this one, you get 1 over ln 3. Differentiate sine, you get cos, and then divide by the whole sine. The third reminder, if f of x is a function e to the power u, to differentiate, you get the derivative of this as the derivative of u first multiplied by e to the power u. An example, or put examples. One, find f prime of x. F of x is equal to e to the power tan x. The derivative of f is going to be, you differentiate tan, and the derivative of tan is equal to sec squared x. So you have sec squared x multiplied by e tan x. Another example, f of x is equal to 2e to the power 3x plus 4. To differentiate f, you have 2 as a constant. When you differentiate 3x plus 4, you get 3, and then multiplied by e 3x plus 4, giving us 6e 3x plus 4. So the e will still come back in the derivative. After that, to differentiate 4, another reminder, if you are differentiating f of x is equal to a to the power u.
Sorry, sir, can I just see the previous page to take a screenshot?
Okay.
Okay.
To differentiate a to the power u, if you have forgotten the general formula, you go the long way. So you say, okay, let me write it in terms of y, a to the power u. And then to drop u from the power, you introduce ln. You also introduce ln the other side. So you have ln y is equal to a, is equal to, remember the properties of log allows us to drop the power. So drop the power u and get ln a. And then differentiate now implicitly. So you differentiate y, ln y, you get the derivative of y is 1 over y itself. And because it's y, we write dy dx, which is equal to derivative of u is 1 multiplied by ln a. So dy dx is going to be y ln a. You cross multiply the y, but y is a to the power u ln a. To see what this means, and examples, differentiate a f of x is equal to 2 to the power 5x plus 1. The derivative is equal to 2 5x plus 1 is the first thing you quote, and then ln 2. But that's not done. There's also the derivative of 5x plus 1, which is 5. This is obtained from the previous section where the power must be differentiated. Why are we saying the power must be differentiated? Because if y is equal to 2 5x plus 1, then we're going to have ln y is equal to ln 2 5x plus 1, which is ln y. We'll drop the power and get ln 2, then differentiate. You have this is equal to 5, derivative of 5x plus 1, ln 2. So dy dx is equal to y 5 ln 2. But y is 2 5x plus 1, 5 ln 2. So that's why it has to come out like this. Another one, if we have f of x is equal to,
Sir,
hello,
can you please repeat? I've not understood that part.
on which section? On the general formula or the simplification?
On example A.
Okay. So you're saying example A depends on this general formula here, coming from the original question. So whenever you are given a function f of x is equal to some constant a to the power function, the derivative of this function, according to this, is going to be a g of x, then g prime of x, then a. This is the formula that we're going to use to give us the derivative. So we just identified our g, which is the power, differentiated it, we got 5, then find the base, and then we keep it as ln 2, and then keep the whole function. Look at this example here, example B. 3 power 2x multiplied by 5 power 4x. This is a product rule. So you let u to be 3 power 2x, let v to be 5 power 4x. Then differentiate u where has u gone on the right side? It has been differentiated. The derivative of u is 1. So here where I put x is supposed to be u. Okay. Then, so we differentiate 3 to the power 2x. We first differentiate the power 2x, we get 2. And then there will be in 3 here, multiplied by the whole function 3 power 2x. The derivative of v, you first differentiate the power, you get 4. Then you multiply by, and in base 5. And then the whole 5 for x will come back. That's what this means here. You differentiate, multiply by the in base, and then the whole function comes back. So that f prime of x becomes u prime v plus v prime u, giving us, this is u prime, so we get 2 and then 3 power 2x multiplied by v, which is 5 power 4x, plus v prime is 4, then 5 multiplied by 5 power 4x, u is 3 to the power 2x. If you want, you can actually factor out the function. Say, okay, 3 2x is common, 5 4x is common, and then we'll have 2 then 3 plus 4 and then 5, like this. So just a reminder on how you differentiate such function.
But why did you use ln in the brackets?
I don't understand by in the bracket.
In the U prime, you wrote 2 in 3. Why did you use in 3?
Because we'd always go for in base. In base. When the function.
Oh.
Okay. Let's click one. Now, a quick revision on the derivatives of logs so that we can then peacefully look at the derivatives of trig inverse functions. Ideally, we want to look at integration. So we need this reverse. We need this derivative so that the reverse will be smooth. And since we have time, we can do it. Derivatives of trig inverse functions. Differentiate a y is equal to sine inverse of x. So let's do sine inverse of the function u. Sine inverse of u. You can as well write this function as y is equal to arc sine u. Okay, so solution. If I have y is equal to sine inverse of u, where u is a function of x, the first thing you do when you have second function, which is a sine inverse, you take the other side as sine. So sine y is equal to u. And then from there, you differentiate, you're differentiating y here with respect to u. So we differentiate y as a function. The derivative of sine is cos. So we'll have cos y and then dy du. When you say dy du, you keep the u. But if we say dy dx, then we also differentiate u on the right with respect to x. So that we'll have then dy dx is equal to u prime divided by cos y. So you divide for you to get the dy dx, which we are looking for. So I've gotten u prime over cos y. But we need to switch this guy. This cos y needs to go back because in our function there's no y. It must be a function of u on the right. As you can see, I'm differentiating this guy to respect to u. So why should the derivative have y? So you need to change that. But we know that taking to u, we know that cos y, cos squared y is the same as from this derivative here. From this identity, sine squared y plus cos squared y is equal to 1. We actually realize that cos squared y is actually 1 minus sine squared y. Now, since we said that u is equal to sine y, then the best option you can use to change cos back to u is to pass through sine. So what is cos in terms of y? Cos y is a square root of 1 minus sine squared y. This can be written as the square root of 1 minus sine y squared. But we just said that sine y is equal to u from here. So if sine y is u, then we'll have u prime over the square root of 1 minus sine y squared. And this becomes dy dx. And we call the derivative of sine inverse.
Sir, I'm lost. My network cut
Okay.
on here from sine y is equal to u.
Sine y is equal to u. Okay. Even for those who didn't ask, when you reach here and say sine y is equal to u, you have not yet differentiated. So you differentiate with respect to u, but we have sine y. So we differentiate y as if it's the only function. The derivative of sine is cos. You fix the y. And then the derivative of y is 1. So you have dy dx to multiply because you have differentiated y. But because I'm differentiating with respect to x, it means that in this u there is also x. So you will differentiate u as well with respect to x. So you just say u prime. Now we're looking for dy dx. So we divide by cos y, we divide by cos y. What we know is that u is equal to sine y. And yet we have cos y here. From this identity, we must solve for cos y. Maybe it will help us get back to u. To solve for cos y, we take sine squared y the other side from this identity here that we named the most important identity. Very, very useful in this area. So we have it here. Now we solve for cos y from here. So first you solve for cos squared, and then you square root the cos squared for you to get cos y is equal to that. Now we have gotten that cos y is equal to 1 minus sine squared under the square root. But we just said here that sine is equal to, sine y is equal to u. So where there is sine y, you substitute u and then bring it here. And you're done. If you are dealing with y is equal to cos inverse u, you say this is the same as cos y is equal to u. So cos y is u. Then we differentiate. The derivative of cos is negative sine. Then dy dx. So that we also differentiate x with this, and we differentiate y with respect to x. And then solve for dy dx. It becomes negative u prime over sine y. We go back to the identity and solve for sine y in terms of cos, because we know cos y is equal to u. So here you get sine y is equal to the square root of 1 minus cos y squared. So we substitute to have negative u prime over, where the sine y, it is the same as the square root of 1 minus cos y squared. So we have 1 minus, so what is cos y? Cos y is u from here. So we'll have u, because it's squared, u will also be squared. So these two are almost the same. They differ by just a sign. Now look at how we apply this. Look at how this is applied. Questions may not come this smooth. They may come in this form. Find y prime. Y is equal to sine inverse 4x squared plus 1. So you say, okay, from this one here, whatever is inside can be written as u. So you say, solution, I know that dy dx for sine inverse is going to be u prime over the square root of 1 minus u squared. So let u be equal to 4x squared plus 1. What is u prime? 8x. The derivative here is going to be 8x over the square root of 1 minus 4x squared okay, 4x squared plus 1 squared. If you want, you can simplify inside, but it's not necessary. So you can just leave it like that. The previous board. So here you just need to pick, after you've known how to, you need first to know how to get to this formula in case you forget somewhere. But in case you have not forgotten, there's no need of driving the whole thing. You just place the formula there and then get the derivative. In everything that you have done here, if you have not forgotten the general formula, you just place it there, you write it, and then substitute in it. Then B, y is equal to arc cos of say 7x plus 3x squared. Again here, when you're dealing with cos inverse, you say, okay, here my dy dx is going to be negative u prime over the square root of 1 minus u squared. So let u be 7x plus 3x squared. And get, let's just write as u prime. U prime will be 7 plus 6x using power rule, of course. And then you say, okay, so my dy dx is as simple as negative 7 plus 6x over the square root of 1 minus 7x plus 3x squared, everything squared. We're done. Nothing complicated. Because it's this easy, you can as well demonstrate that derivative of y is equal to tan inverse of u. Should also be an easy thing to do. Say tan y is equal to u, you keep that one there, and then differentiate it. So differentiate tan y, we get sec squared y dy dx is equal to u prime. So you have dy dx is equal to u prime over sec squared y. But look, what we have here is tan. So you say, since I have tan, am I able to change sec to tan? Of course, yes. We know that sec, we know it in this way. We know that 1 plus tan squared x is equal to sec squared x. So since we have sec squared y here, then we're going to write u prime over 1 plus tan squared y. But tan is what we have called as u. So we'll have u prime over 1 plus u squared. So that if you're given a question to integrate, say y is equal to tan inverse of 3x. Your solution, the easiest thing, you just differentiate 3x, you get 3, and then divide by 1 plus 3x squared, which will be 3 over 1 plus 9x squared as your solution. We have questions? Remember that we don't invest time in sec inverse, cosec inverse, or cot inverse, because when those come, you treat them as using the other guys. The sec inverse will be the same as is it the same? In fact, those you already asked because they are very, very complicated. The derivatives are not nice. So we only deal with these basic 3. So this was a recap. But for the inverses, it was a new thing. And we have done it in a smooth way. So that as we log out and log back, we are now going straight into integration. We hope to finish it today.
So,
Yes,
what are
hello?
we looking at? I joined late.
Okay, so we are
I'm
just
saying, what are
doing,
we looking at? I joined late. I want to write the subtopic.
okay, the best subtopic you can write is integration.
Okay, thank you.
But before that, we had a recap of derivatives of logs and exponentials and derivatives of trig inverse functions. So that now we use these. If we meet them somewhere in integration, we must not forget that we have such a thing. Don't worry about that complication.
So I'm just requesting for the last night. Yeah,
It's here. So let's log out and be back quickly.
Sir, so for question D, you don't say 3 by 2, but 3 squared.
Yeah, 3 squared. This is u squared. So you square the 3. You get 9.